So number 3, this one has a current going in. It has a loop with current going clockwise. I'll call that I1. I have a wire with current going from left to right. I'll call that I2. And then I have another current out here with current coming out. Okay. And the question is, what is the net magnetic field at the center of the loop, right here? What is the net magnetic field right there due to all of those currents? What is going to be my net magnetic field here at this point? Okay, so can I make use of the superposition principle? Can I break it up into 4 different pieces?
Yes.
I can. So let's do the loop first. Let's find the magnetic field of the loop first. Alright, so I'm going to redraw it. So here it is. Here's my loop. And I'm going to have current I1. And here's my point P. Okay. This is the point where I want to find, I call it C here. Let's just call it point P. Point P is the point where I want to find the magnetic field. Alright, so first off, direction. Okay, so I'm going to use this guy as an example. So this is my loop, and I have current flowing clockwise in that loop. And I want to calculate the magnetic field right there at the center of that loop. So, right-hand rule 1 or 2 to get the direction of a magnetic field? 1. Okay, so does everybody agree that in this case it doesn't matter where I test it? It doesn't matter where I put my thumb. As long as my thumb is in the direction of the current. Does everybody agree that I can test it here, here, or here? Does everybody agree? So let me test it here at the bottom. So my thumb would be in the direction of the current, right? So here it is, and I'm going to curl my fingers almost like I'm going to grab onto the bottom of that loop. So when I'm inside of that loop, which way are my fingers pointing? In, and when I'm below, it's pointing out. So that means that inside of the loop, the magnetic field is in, and outside of the loop, the magnetic field is out. Now, question for you. Do the field lines actually look like this, or is this just, if you were to rotate this on its side, what would it look like at that point? So let's try that again, because that's something you may have to draw tomorrow. Does everybody agree that if I were to rotate, does everybody agree? Imagine this as being the arrow of that current. Does everybody agree the current's going this way? Does everybody see that?
Yeah.
If I were to rotate it into this perspective, does everybody agree that current would be flowing into the board at that point? Does everybody agree? So let's draw it. Does everybody agree that it would be into? But now watch this. Current goes around, and from the bottom it comes out. Does everybody agree with that statement?
Yes.
Everybody see that? So now let's apply right-hand rule in this new perspective. Take your thumb, put it in the direction of the current. That's into the board. Curl, which way am I curling? Clockwise. Does everybody see that? Now, question. Do the field lines actually terminate, begin here and terminate here? No, because they loop around. So this would continue all the way around and back to here. This is the only one that actually extends to negative infinity and comes back from positive infinity. Okay, now let's do the bottom one. Let me just erase this for a second. The bottom one, I have current coming out. So I'm going to go ahead and put my thumb out this time. Curl, which way am I curling now? Counterclockwise. Excellent. Now this tells us more than this picture. Does everybody agree that here immediately you would be able to tell which side is north and which side is south? Which side is north? Left. And which side is south? And does everybody see that that looks just like a dipole field? Does everybody see it? It looks almost like the magnetic field of a bar magnet. North-south. Looks something like this. Now, according to this picture, the one I'm drawing here, it almost makes it seem like the field actually originates at the north and terminates at the south. Is that a true statement or a false statement? False, because they actually form loops. So even inside, look at this. I have field going from one end to the other. So these are actually forming loops. Take a look. So does everybody see how it comes out here goes back in through the south, and then goes back from south to north inside. Does everybody see how they're just loops, even inside? Does everybody see that? All right. So now, here's the thing. Inside of here, since point P is inside, and the magnetic field, we just determined that it was into the board, would that be negative k hat or positive k hat? Negative k hat. That's the negative z direction. So my B1, magnitude. So this is the magnetic field of a loop. So that's going to be mu naught I over 2r. Okay, this is the one without the pi, remember. We derived this one. Remember. So the derivations are also important, so remember to look through those as well. Okay, so mu naught, 4 pi times 10 to the minus 7. The current, how much current do I have flowing through this guy? I1, 16 amps, very good. Divided by 2 times r, what does r represent? It represents the radius of that loop.
60.
Oh, 60. Okay, thank you. And then what about the radius of the loop? The radius is given, it's 10 centimeters, so 0.1. Okay, so let's plug that in, see what we get. So that's going to be 4 pi times 10 to the minus 7 times 60, and we're going to divide by 2 times 0.1. So I have 3.77 times 10 to the minus 4 Tesla. But that would be in what direction? Excellent. Negative k hat. Excellent. Very good. All right, so does everybody feel comfortable with the first part? Is everybody good?
So
Yes.
to get it in that form, which way did you rotate the picture?
It really doesn't matter. I mean, I rotated it like this. But you could rotate it like this if you want. Yeah. It doesn't matter.
So it just matters what current's at.
Yeah, it doesn't matter. Because, I mean, depends on perspective. How it will look depends on how you turn it. Right? Yeah. Okay, so take a look at this. So now I'm going to calculate the magnetic field of the bottom wire, I2, and how much current is running through that wire? 20 amps, right? And I want to calculate the magnetic field here, at this point here. So first direction. If I want to find the direction, is that going to be right hand rule 1 or 2? 1. So I'm going to place my pen like this, parallel to the wire. I'm going to put my thumb in the direction of the current, and I'm going to curl. So when I'm below the wire, which way is it pointing? In, and when I'm above? Out. So that means that below, it's going to be in, and above, it's going to be out. And again, this is just a cross-sectional view of something that's actually going on in 3D. So if you were to actually rotate this wire, if you rotate it like this new perspective, do you agree with me current's coming out? Do you agree? So in that new perspective, thumb is in the direction of the current. Curl, which way are you curling? Counterclockwise. So that is what it actually looks like when you look at it from a different perspective. But this is a cross-sectional view of that. Okay, so you're here. This is you looking at it here, in this perspective. Does everybody agree from the top, field lines are coming towards you? Does everybody see that? And on the bottom, field lines are going away from you. Does everybody see that? Yes or no guess? Yes? Okay. All right, so now, at point P, we're going to calculate the magnetic field. So we have B is equal to mu naught I over 2 pi r. Why is there a pi now in this one? Because this is a straight wire, right? So we have mu naught, which is 4 pi times 10 to the minus 7. I is 20. That's 20 amps. Divided by 2 pi times the radius. The radius in this case is the distance to the point P from the wire. So that's 0.2 meters. That's given. So that's 0.2. That's going to be 2. Let's see. That's going to be about 5, I think. 2 times 10 minus 5. Yeah. Tesla. And since it's pointing out, what do we call that? Positive z direction, right? So that's going to be the positive k hat direction. All right. So now we're halfway there. So now we're going to calculate